Hello everyone, I am Danish and today I am going to walk you through a really interesting paper from ICSE 2026 called On Interaction Effects in Greybox Fuzzing. This is a paper from University of Zurich in Switzerland and Max Planck Institute for Security and Privacy in Germany. The big question this paper asks is very simple. When a fuzzer applies a sequence of mutations to test input, does the order of those mutations matter? And if it does matter, then can we exploit that to find more bugs? So we'll start with the background you need, what fuzzing is, how mutation strategies work. Then we'll get into the key insight of this paper, that there's a measurable interaction effect between mutators. After that, we'll see how the authors exploit this with their tool MoveFuzz, look at the evaluation results, and wrap up with a critical discussion of strengths and weaknesses. I'll be asking you questions along the way, so stay with me. Alright, so let's start from the beginning. Fuzzing, what is fuzzing? It is an automated software testing technique, and the core idea is really simple. You throw a bunch of weird, unexpected, random inputs at a program and see if anything breaks. Look at this pipeline on the slide. You start with the seed input. This is a valid input that the program normally accepts. For example, if you're testing a PDF reader, your seed might be a real PDF file. Then you mutate that seed, flip some bits, delete some bytes, insert some junk, etc. You feed this mutated input to the target program and watch what happens. So two things can happen that we care about. First, the program might crash. That's potentially a bug. Maybe even a security vulnerability. Second, the input might reach new code that we haven't seen before. We call that a coverage increasing or interesting input. And when we find an interesting input, we add it back to our seed corpus so we can mutate it further in future rounds. This feedback loop is the key, and by repeating this millions of times, the fuzzer gradually explores deeper and deeper into the program's code. Now here's a question for you to think about. Why would random, garbled inputs find bugs that careful human-written cases miss? The answer is that humans tend to test the expected. We write tests for how the program should behave. Fuzzers test how the program actually behaves when given inputs nobody ever anticipated. And that's where the surprising bugs hide. Now, not all fuzzers are created equal. There's a spectrum. On one end, you have black box fuzzing. You know nothing about the program's internals. You just generate random inputs and hope for the best. It's fast, but it's dumb. On the other end, you have white box fuzzing, which uses heavy program analysis like symbolic execution. It's very precise. It can reason about exactly which inputs will trigger which code paths. But it's computationally expensive and doesn't scale well to large programs. Greybox fuzzing sits in the sweet spot in the middle. It uses lightweight code coverage feedback. Basically, it instruments the program to tell you which branches were taken without doing full program analysis. It's fast enough to run millions of inputs per second, but smart enough to steer toward unexplored code. And the most widely used Greybox fuzzer is AFL++. If you work in security, you have almost certainly heard about it. So now let's zoom into the part of fuzzing this paper focuses on, the mutation strategy. So when AFL++ decides to mutate a seed, it doesn't just apply one change. It applies a sequence of mutators, anywhere from 2 to 16 of them, stacked one after another. So your seed goes through mutator 1, then mutator 2, then mutator 3, and so on. The result of the whole chain is your mutated input. Look at the example on the slide. We start with the seed, apply, let's say, flip a bit, then delete a block of bytes, and then insert some bytes. Each mutator transforms the output of the previous one. This sequence, this ordered list of mutators, is what they call a mutator sequence. Now here's a critical question. How does AFL++ choose which mutators go into the sequence? And the answer is straightforward. Maybe too straightforward. Each one of 32 mutators has a fixed predefined probability. AFL++ just rolls the dice independently for each position in the sequence. Mutator 1 doesn't care what mutator 2 is. Mutator 3 doesn't know what came before it. Every choice is independent. MOPT or MOPT, which is a prior work from Unix Security 2019, improved on this by learning better probabilities for each mutator. Mutators that produce more interesting inputs get higher probabilities. But, and this is the crucial part, MOPT still treats each mutator independently. The probability of picking the next mutator doesn't depend on what you picked before. Think about that. We are applying these mutators in a sequence, one after the other, and yet we are choosing them as if they have nothing to do with each other. That's the gap this paper identifies. So before we go further, let me give you a quick tour of what these 32 mutators actually do, because it'll help you understand the interaction of it. They fall into two families. On the left, you see the unit mutators, IDs 1 through 20. These are the surgical lightweight operations. Flip a single random bit, replace a byte with a so-called interesting value. These are values like 0, 1, -1, max, int that tend to trigger edge cases. Add or subtract a small number from a byte or a pair of bytes. These are small, precise tweaks. On the right, you have the chunk mutators, IDs 21 through 32. These are heavy hitters. They operate on whole block of bytes. Delete an entire block, swap blocks between two positions, grab a block from a completely different seed and splice it in. Overwrite a block with dictionary entries. These are disruptive structural changes. Now here's a question I want you to hold in your mind. Does it matter if you apply a unit mutator first and then a chunk mutator, or a chunk mutator followed by another chunk mutator? Intuitively, you might think it does. A small tweak followed by a big restructuring is a very different operation than two big restructurings in a row. And that's exactly the intuition this paper formalizes and tests. Okay, so here we are at the core of the paper. Let me lay it out clearly for you. On the left side of the slide, you see the current approach. AFL++ and MOPT both do the same thing. They sample each mutator from a probability distribution independently. M1 is drawn from PR of M, M2 is drawn from the same probability of M, M3 is drawn from the same probability of M. The choice of M2 has absolutely nothing to do with what M1 was. It's as if you are rolling a die each time and each roll is completely separate. On the right side, you see what this paper proposes. Instead of drawing each mutator independently, you condition on the previous one. M1 is still drawn randomly, but then M2 is drawn from probability of M given M1, and M3 is drawn from probability of M given M2. The probability of the next mutator depends on what you just did. And this is a fundamentally different model. Instead of treating the mutator sequence as a bag of independent choices, we are treating it as a chain, where each step influences the next. If you have taken a probability course, you'll recognize this as a Markov chain. If you studied NLP, you'll recognize it as a bigram language model. Same math, but just different domain. So the hypothesis is clear. How do we test it? The authors do this in 3 clean steps. First step is collecting the data. They run AFL++ on 13 real-world target programs from the Fuzzbench benchmark. But they make 3 key modifications. First, they fix the mutator sequence length to exactly 2. So every sequence is just a pair. Mutator I followed by mutator J. Second, they sample mutators uniformly at random instead of using AFL++'s default probabilities. So they get equal amounts of data for every pair. And third, they maintain a 32 by 32 matrix and that counts how many interesting inputs each pair produces. And they run this for 20 trials per program. Second, they fit a linear model, and the model is n hat of ij equals mu plus alpha I plus beta j plus gamma ij, where mu is a constant baseline. Alpha I captures the effect of mutator I being first, regardless of what comes second. Beta j captures the effect of mutator j being second, regardless of what came first. And gamma ij is the interaction term. It captures the extra effect of combining I with j specifically. If gamma is 0 for all pairs, there is no interaction effect. Step 3 is they run a two-way ANOVA, which is analysis of variance. This is a standard statistical test that asks, does the interaction term explain a statistically significant portion of the variance in the data? In other words, do we get a significantly better model when we include the interaction term? The answer, p-value of less than 0.0001 for every single program. The interaction effect is real and highly significant. This is their first finding, and it's the foundation everything else builds on. Now let me help you visualize what the interaction effect actually looks like. Imagine a 32 by 32 heat map. Each row is the first mutator, each column is the second mutator. The color of each cell tells you how many interesting inputs that pair produced. The paper shows these heat maps for each target program, and a fascinating pattern emerges in most of them. Look at the schematic on the slide. When the first mutator is a unit mutator, one of those lightweight surgical operations, the second mutator is much more likely to produce an interesting input if it's a chunk mutator. The cells in the upper right quadrant light up. A small tweak followed by a big structural change is a powerful combination. But when the first mutator is a chunk mutator, a big structural change, then this distribution for the second mutator is roughly uniform. It doesn't matter as much what comes next after a big disruptive change. This pattern holds in 9 out of 13 programs. The other 4 show different patterns. For example, in OpenSSL, unit mutators dominate, probably because the input format is strict and chunk mutators tend to break it. In libpcap, arithmetic mutators work well when stacked on top of each other. And the key takeaway here is there is structure in the data, and it varies by program. This is exactly what you'd want to see if you're going to build a program. Adaptive mutation strategy. As a complementary piece of evidence, the authors compared the goodness of fit of the model with and without interaction term. The bar chart on the slide shows the improvement in adjusted R squared when you add the interaction term. Look at the bars. For program like JSON and RE2, the improvement is massive, over 0.2. For proj4 and curl, it's substantial at 0.09 to 0.14. For programs like SQLite and libxml, the improvement is small. And this correlates beautifully with the later results. MoFuzz improves the most on the programs where the interaction effect is the strongest, and improves the least where it's weakest. And this is one of the strengths of the paper. The theory and the practice are consistent with each other. Okay, so the interaction effect is real. Now what? The authors built MoFuzz. That's mud plus duo plus fuzz to exploit it. It's a two-phase approach built directly on top of AFL++. Phase 1 is the training phase, and it takes 1 hour. During this time, MoFuzz runs AFL++ with the same 3 modifications from the experiment. Sequence length fixed at 2, uniform random sampling, and tracking the matrix N. So the first hour of every fuzzing campaign is essentially data collection. At the end of that hour, mu_fuzz normalizes each row of the n matrix. It divides each entry by the sum of its row, turning each row into a proper probability distribution. Now for any mutator I, you have a distribution that tells you, given that I was the previous mutator, how likely is each mutator J to produce an interesting input as the next one. Phase 2 is the guided mutation phase, and it runs for the remaining 23 hours. Now when mu_fuzz needs to generate a mutator sequence, it picks the first mutator uniformly at random, and then for each subsequent position, it samples from the conditional distribution learned in phase 1. It's a random walk on a Markov chain. Each step depends only on the previous step. What I love about this design is how simple it is. There are no neural networks, no complex optimization. Training is literally just incrementing a counter. And yet, as you'll see, it works. So let me make the connections to things you might already know. The slide shows mutators as states in a Markov chain, with transition probabilities between them. Starting from any state, you look at the outgoing probabilities and randomly jump to the next state based on those probabilities. The authors themselves point out the connection to bigram language models in NLP. In a bigram model, you predict the next word based only on the previous word. Here you just predict the next mutator based on the previous mutator. Same mathematics, different application. And this opens up a really exciting research direction, which we'll talk about at the end. What if you used more powerful sequence models like RNNs or even transformers to generate mutator sequences? Could you build GPT for fuzzing? It's a fun thought. So the authors made several design choices that are worth understanding. First, why only condition on the last mutator? Why not the last 2 or the last 5? Then the answer is curse of dimensionality. With 32 mutators, pairs give you 1024 entries in your matrix. Triplets give you 32,768. Most of those triplets will never produce an interesting input during 1 hour training phase, so you can't learn meaningful probabilities. The authors did try it. The p=2 variation performs worse in every single program. Second, sequence length. AFL++ uses a fixed distribution from 2 to 16. mu_fuzz instead uses an epsilon greedy multi-armed bandit to dynamically choose the length. It starts by exploring all lengths equally, then gradually exploits the best performing length. This helps in 9 out of 13 programs. Third, how to pick the first mutator. You might think a weighted selection favoring mutators that have been more productive would help, but actually uniform random selection works better. The author's interpretation is that weighted selection makes the sequence too deterministic, reducing exploration. This is a nice reminder that in fuzzing, randomness is a feature and not a bug. And finally, training time. 1 hour is the sweet spot. Half an hour doesn't give enough data. 2 hours wastes time that could be spent in more effective guided mutation phase. Now for the results. The evaluation uses FuzzBench with 13 real-world C programs, running each fuzzer for 24 hours with 30 independent trials. That's a lot of compute, over 28,000 CPU hours just for this experiment. The headline numbers: mu_fuzz achieves the highest coverage in 9 out of 13 programs compared to AFL++, and 8 out of 13 compared to mock. These aren't just higher, they are statistically significant by the Mann-Whitney U-test. But here's what I think is the most compelling number. mu_fuzz reaches AFL++'s final 24-hour coverage in just 15 hours on average. Think about that. It takes AFL++ 24 hours to get a certain coverage level, and mu_fuzz gets there 9 hours earlier. Given that the cost of discovering new branches grows exponentially over time, this is a massive speed up. Now where does mu_fuzz not help? In programs like libpng and OpenSSL, and these are exactly the programs where ANOVA analysis couldn't confirm a strong interaction effect, or where the linear model had a poor fit. The theory predicts the practice. When there's no interaction effect to exploit, more fuzz doesn't improve, and it doesn't make things worse either. The JSON program is an interesting edge case. All three fuzzers reach maximum coverage of 520 branches in just 15 minutes. The mutation strategy simply doesn't matter there. Coverage is great, but the real goal of fuzzing is finding bugs. The authors use the Magma benchmark, which contains real-world bugs that have been manually ported to the latest versions of 8 programs. The results: MoFuzz found 4 bugs that AFL++ missed entirely. AFL++ found only 1 bug that MoFuzz missed, and that one was found in only 1 out of the 20 trials. So it was likely just lucky randomness. The comparison with MOP is more nuanced. They find the same total of number of bugs, but each found one unique bug the other missed. MoFuzz found SQL010 that MOP missed. MOP found SSL001 that MoFuzz missed. And here's the beautiful thing. SSL001 is in the OpenSSL program, the one where we already know the interaction effect is weak. So even the bug MoFuzz misses is consistent with the theory. The differences in average unique bugs per trial aren't statistically significant, which the authors honestly report. This is a limitation, but the pattern of unique bug discovery, MoFuzz triggering different program behaviors, suggests that exploiting the interaction effect does something qualitative different from just optimizing individual mutator probabilities. The ablation study is one of the strongest parts of this paper. They systematically test every design choice. When they replace the learned N matrix with a completely random matrix, performance drops in all 13 programs. The performance comes from the learned interaction probabilities and not from some side effect of the two-phase design. Using p=2 context, conditioning on the last two mutators instead of one hurts in all programs. The sparsity ranges from 0.003 to 0.1, confirming the curse of dimensionality. Default sequence length hurts in 9 of 13 programs. Weighted first mutator hurts in 10 of 13. Training time of 1 hour is better than 0.5 or 2 hours in most programs. They even test cross-program generalization. Take the probability matrix learned on free type and use it on other programs. It works reasonably well for 9 programs that share a similar pattern, but fails for the 4 programs with different patterns. This tells us the interaction effect is somewhat program specific, which justifies the per program training phase. Let me give you my assessment of the paper's strength. First, they don't just say we made a better fuzzer. They identify specific measurable phenomena, the interaction effect, and they test it rigorously, and then build a tool that exploits it. So the scientific methodology here is solid. Second, the evaluation is thoroughly by fuzzing standards. 30 trials per program, 24 hours each, statistical tests with effect sizes, 2 different benchmarks. This follows all the best practices recommended for fuzzer evaluation. And third, the ablation study is comprehensive. Every design choice is tested. The random matrix baseline is particularly convincing. This is the kind of thing reviewers love to see and many papers skip. Fourth, the paper is aware about its limitation. It explains exactly why and when MoFuzz doesn't help, and the explanations are consistent. Fifth, the approach is simple and practical. Training is just counting, no GPU required, no neural network to tune. You could implement this in a weekend. Now let's talk about the weaknesses. The biggest one, in my opinion, is the static training phase. The probability matrix is learned in the first hour and then frozen for the remaining 23 hours. But the seed corpus evolves dramatically during a fuzzing campaign. The mutator pairs that are effective early on when you are exploring shallow code might not be the same pairs that are effective later, when you are trying to reach deep, hard to reach code paths. And the authors acknowledge this indirectly. They tried moving the training phase later and saw worse results because there's less training data. but they don't explore dynamic retraining. Second, they only model pairwise interactions due to the curse of dimensionality, but real mutator sequences are 2 to 16 mutators long. Patterns like flip a bit, then delete a block, then insert a dictionary entry might be more effective than any pair suggests. Uh, Third, the program selection. They use 13 of 28 fuzzbench programs. Uh, they take the union of programs from two recent papers. It's still a subset. They also couldn't include seam fuzz as a baseline because of version incompatibility, which is just unfortunate. Finally, the coverage results are statistically significant. The bug finding differences are not. The average number of unique bugs per trial doesn't differ significantly between fuzzers. This is common in fuzzing research. Bugs are rare, noisy events, but it does weaken the practical significance claim. Finally, let me leave you with four key takeaways. Mutator order does matter. The interaction between consecutive mutators is statistically significant and can be measured rigorously. Second, simple ideas can be powerful. MuFuzz's training is literally just counting pairs and dividing by a sum. No fancy math, no deep learning, no complex optimization. And yet it beats both EFL++ with its fixed probabilities and MOP with its particle swarm optimization. Third, theory predicts practice. When the interaction effect is strong, MuFuzz improves. When it's weak, it doesn't. This consistency between theory and experiment is the hallmark of good empirical research. Fourth, the bigram language model connection opens a whole new research direction. If treating mutator sequences like bigram text generation works this well, there's a lot of headroom for applying more sophisticated sequence modeling techniques. Thank you.